In the previous video, we learned how to add two vectors by positioning them tip to tail, making a triangle or a parallelogram, and using law of sines and law of cosines to find missing sides and angles. Now we're going to look at using vector components. Vector components will allow us to use right triangle trigonometry to accomplish the same thing that we did previously. So let's define a few terms. Number one, unit vector. A unit vector is a vector that has a length of 1. Specifically, we want to identify two vectors. A vector that has a length of 1 in the x direction, which we'll call I, and a vector of unit 1 in the positive y direction, which we'll call j. X and j, or I and j, go with x and y, alphabetical order, and both j and y have a tail on them, so that's kind of helpful to help remember. We can also use vector k as a unit vector in the positive z direction if we have a 3D vector, and we're going to look at that, one of those, in just a minute. Now, if we multiply the unit vectors, by a number called a scalar, we can change the scale of the vector, or the length of the vector. So if we have a vector that has I in it, it's still going in the x direction, but then the number in front tells us how long the vector is. So this is a vector of length 4 in the I direction. And the negative 5 tells us this is a vector of length 5 in the negative x direction. So this should be positive x direction, negative x direction. And then 3j tells us we have a vector of length 3 in the positive y direction. Now these are known as, these when put together can be the components of another vector. So when we add them together, 4i plus 3j, I'm going to draw, here's my vector 4i, here's the vector 3j. Now when we add vectors, we have to add them tip to tail, so we can move the 3j over here, and then starting at the origin, draw from the beginning of one vector to the end of the second vector, and this is our vector v. This vector is the sum of these two vectors. Now because this is going in the positive x direction and this is in the positive y direction, they are perpendicular to each other. We have a right triangle. These two vectors, 4i and 3j, are known as the components of vector v, the horizontal and vertical components. Vector w would be a vector in quadrant 3 because its two components are both negative. We have negative 5i and we have negative 3j. And when we move them tip to tail, we're going to move the y vector. Now somebody might say, well, could we move either the x or y? Yes, you can move either vector to add, but we specifically want to move the y vector because we want to make a right triangle whose adjacent side is on the x-axis so that we can do the kind of trigonometry we've been doing in many of our other units. So we want to leave the I vector alone and move the j vector over to make a right triangle. So here's our vector w. Now I'll come back to the three-dimensional vector in just a second. What's nice about this is now we have a right triangle. We have the vector v as the sum of two component vectors, vector xi and vector yj, where x and y are the length of the vectors. So when we use component vectors, the sum forms a right triangle. Okay, so here we have our three vectors. Here's the vector, and these two are the component vectors. In other words, we're splitting this vector that's kind of going in a diagonal direction into its two vectors in the x and y direction that add up to that vector. Now, if I look at just the length of the vectors, so these are the vector lengths in this little triangle, you can see there's the length of vector v, and then x and y are the lengths of the two components. Now I can now use any right triangle methods I want to use. I can say x squared plus y squared is the square root, or sorry, the length of v squared, length of vector v squared. I can say cosine of theta is equal to x over the length of vector v. I can say sine of theta is y over the length of vector v. And I can say tangent of theta is equal to y over x. And all of those relationships are going to help me to move from either components to angle and direction, or from angle and direction to components. Now before I summarize that, let's go back and just take a look at what a 3D vector would look like, just for fun. I changed this one to 4K, although that might be already corrected in your notes. And I'm going to say I have vector, this is my vector that's moving in the x direction. Here's my vector that's in the y direction, and here's my vector that is in the z direction. Now, when I have a three-dimensional vectors, I have to picture that x and y are flat on this plane, and vector x is actually sticking out from the paper. So I'm going to show you what that looks like. So imagine x and y, or y and z, sorry, are flat against the paper, and here's vector x sticking straight out from the paper. So that's what you have to picture, is that the x-axis is actually sticking straight out from the paper and back into the paper. Now, returning to my drawing here, I'm going to use, I'm going to draw my vector 4 units long in the x direction. So notice I have little tick marks here, 1, 2, 3, 4, to indicate how long the vector should be. And then this would be 1, 2, 3 in the y direction. So I'm using every 2 boxes to make 1 unit, because it ends up, when I look at the perspective, it ends up looking better that way. So there's vector in the x direction, vector in the y direction. There's this is 3j over here, and this is my vector 4i over here. Now if I added those two together, I could add those tip to tail by moving my j vector 1, 2, 3 right here. I could move 1, 2, 3. I could move that there, and I could also move my 4i vector to the tip of my 3j vector. So the sum of these two would be the diagonal of this parallelogram. But I'm not done yet. I still have to add the 4k. So the 4k goes straight up 4 units on the z-axis. So if I wanted to add that to the 2 that I've already have, so I've got x plus y and then plus z, I'd have to go up 4, 1, 2, 3, 4, from the tip of the 3rd vector. So the sum is actually going to go from the beginning of the x vector to the end of the z vector, from here to here. And I'm going to draw this in with a green vector to show you make sure I've got it green. There is the actual vector sum. Now I want to show you a little more framework to show what that actually is. So you can imagine that, okay, if this is sticking out straight out, that this is kind of sticking out at an angle from the wall. So we've gone forward 4, to the right 3, and then up 4, and so this is sticking out at a diagonal. Now we talked about if we add together 2 vectors, the sum is the diagonal of a parallelogram. If we add 3 vectors, what does that represent as far as a geometric figure? So I'm going to add in a few more lines. I'm going to add vector z up to from every corner here. So there's another vector, my z vector, 4k. Here's another one, 1, 2, 3, 4. So here's another one. Now I'm going to connect the sides of this top with the other 2 vectors. So I have my vector 4i that goes this direction, and I have my vector 3j that goes this direction. So notice where all the tips meet, that is where no matter what path I take, I could add k plus I plus j, I could add I plus k plus j. I could add I plus j plus k. No matter how I add them, I always end up here. And the resultant vector is actually the diagonal that goes from the back bottom corner of the box to the front top corner of the box that sticks out away from the wall. If you can imagine that coming out towards you, that would be the physical meaning of a three-dimensional vector. And it turns out 3, 4, 5, even multiple dimension vectors can be used to represent a lot of quantities in real life. I've even heard of a new technology in which vectors are being used to help increase the streaming time of video over the internet. And I'm not sure how that works, but it's supposed to be superior to using just the pixels. It takes up less room, and it increases the streaming time, but I'm not quite sure how it works. Vectors are also used to represent quantities that just need to be added together, sometimes in other applications that you wouldn't even think of as a geometric figure necessarily. So summarizing here, one more thing. There's another way to name a vector, and that is I can take if I have a vector that has a tail at the origin, I can go to its tip and just use the coordinates of that point. In this case, it would be 4, 3, and label the vector. But I use V-shaped brackets to indicate that this is a vector and not just a point. So this would be -5, -3, and this one would actually be labeling that point 4, 3, 4. Okay, so now that I've shown two different ways, so here are our vector components, xi and yj. This is how we represent the magnitude or the length of the vector and the direction theta. Here are the two different ways we can write a vector. So we have two situations here. If we're given the vector's length and its direction, we can find its components using sine and cosine. Basically here solving this equation for x and this equation for y. If we're given the components of the vector, so we know what x and y are, we can find its magnitude and direction using the Pythagorean theorem for the magnitude and inverse tangent to find theta. Now, if we have an angle that is not in quadrant 1 or 4, because inverse tangent will only give me angles from -90 to 90, if you recall from previous unit, then I have to add 180 to get the angle from quadrant 4 to quadrant 2, or from quadrant 1 to quadrant 3. And if I get a negative angle in quadrant 4 and I want a positive angle, I can add 360. So we'll look at some examples of this. Move to the next page. Sorry, sometimes I have to pause and able to move my page where I want it to go. Okay, so here's one example. I'm given the magnitude and the direction. I'm trying to find the components. We always start by drawing a picture of the vector we're given. So here's 210 degrees. Here's the length of the vector. So this is vector A right here. I want to know its components. I want to know its horizontal component, and I want to know its vertical component. This would be y, and this would be x, and my goal is to write vector A like this. A is equal to something I plus something j, or vector A is equal to, and I have my two components like this, but I need to know what those two numbers are. So I can say cosine of 210 is equal to x over 8. So x equals 8 times cosine of 210. Sine of 210 is equal to y over 8. So y is equal to 8 sine of 210. Now some of you are probably going, wait a minute, this is a 30-degree angle, this is a 30, 60, 90 triangle. Don't I want to use 30 in here? Don't I want to say cosine of 30 is x over 8? Sine of 30 is y over 8. So we're going to explore that for a minute and see why it's best to use the original angle. Here I've calculated 8 cosine 30 and 8 cosine of 210. Notice they're the same number, but 8 cosine of 210 is negative and 8 cosine of 30 is positive. Same thing with sine. We get the same number, but one's positive and one's negative. So if we go and look at our picture, we should notice that in quadrant 3, both quantities should be negative. So the negative answers are the correct numbers. Now, if you decided to use 30, you would get the correct number, but you would have to remember to make it negative. if you are not careful, it's easy to make a careless mistake and put the wrong sign, S-I-G-N, on the number. Okay, so y is equal to -4. So I would have -6.9i minus 4j, or -6.9. I probably should call it in 6.93 here, at least give another decimal point, -4. So there would be what I'm looking for, is to write the sum of the vector in terms of its components. Now sometimes I'm given the components and I want to find the magnitude and direction. So I go to -6. Here would be one vector. My other vector would be +2. So I could go 2 in the y direction, but remember I have to shift the y over and add it to the tip of x. So my resultant vector would be here. So I have -6 and +2. I want to know how long the vector is. I want to know the magnitude of vector b, and I want to know this angle. So the first thing I can do is use the Pythagorean theorem to find the magnitude of the vector. It's the square root of 2 squared plus -6 squared, which is the square root of 40. The square root of 40 is somewhere in between the square root of 36 and the square root of 49, somewhere in between 6 and 7. Turns out to be about 6.32. I don't have any units on there, so I'll just say units. And then to find theta, I can say tangent of theta is 2 over -6. So inverse theta is equal to inverse tangent of 2 over -6, which turns out to be -18.43 degrees, which is clearly not the angle I'm looking for. -18.43 happens in quadrant 4 when I have -2 over +6. I get the same trig value. So this angle is -18.43. It's exactly opposite to the angle that I'm looking for. So to find the angle in quadrant 2 that I'm looking for, I have to take 18.43 and add 180, which gives me 161.57 degrees. So I can say vector B is 6.32 units at 161.57 degrees. So that would be the answer to that. Now, why do I like components so well? In addition to being able to use right triangles, which is nice, there's a really nice feature of components. In order to add two vectors, all I have to do is add their components. So here's vector v, 8i plus 5j, and vector w, -6i plus 2j. If I add their components, I end up with 8i minus 6i is 2i, 5j plus 2j is 7j. So I'm going to show that if vector v is 8i plus 5j, so I'm going to go over 1, 2, 3, 4, 5, 6, 7, 8 in the x direction, and then up 1, 2, 3, 4, 5 in the y direction. I'm just going to use dotted lines. Here would be my vector v. This is vector v. Now if I go left 6, 1, 2, 3, 4, 5, 6, so that would be going to the left 6 and up 1, 2, then my vector w goes from here to here. So there's w. Now the sum of those two vectors would be 2i plus 7j. So if I go over right 2 and then up 1, 2, 3, 4, 5, 6, 7, and I draw a vector to there, that would be the vector v plus w, according to adding the components. Now notice, if I were to take vector v and move it perpendicular to itself and form a parallelogram, look where it ends up. And vector w, and move it parallel to itself, there we go. That confirms what I already knew to be true from the components, or already had been told you that was true, that those are the sum. So this makes it easy to really add up multiple vectors together. If I have three vectors, I would have had to do the parallelogram, find the resultant vector, then do another parallelogram and find another resultant vector, and that gets messy. So Here all I have to do is take all three components and add their x components, and add all three vectors, add their x components, and add their y components. So here I would have 10, negative 10 plus 2 plus 7 plus 2, this is negative 1. 3 plus 9 plus negative 8 is 4. So these are the x and y components of the resultant vector. So if I go over negative 1 and up 1, 2, 3, 4, this is the component vector. So adding the other three vectors together, that's what I end up getting. So using components is really simple for vector addition.